Hi everyone, thank you for coming to my virtual talk. I wish I was enjoying the sunshine in Sardinia. Instead, I'm enjoying the snow in Glasgow. As they say, each to their own. I would like to thank also my co-authors at the Center for Medical Industrial Ultrasonics at the University of Glasgow. This work was carried out as part of UltraSurge, which is a 6.1 million 5-year medical research project looking into miniature high-power ultrasonics tools to be used in robotic surgery. However, ultrasonic surgical tools miniaturization present several interrelated challenges. My talk today investigates the possibility of using piezoelectric single crystals in a traditional Langevin-style transducer. One of the many advantages of robotic minimally invasive surgery is the use of energy surgical tools, which have different effects to the tissue they are applied to. Among these, ultrasonic actuated instruments have several advantages compared to standard electrocautery, including fast dissection and hemostasis and high precision. The harmonic case shown here is the only ultrasonic tool compatible with the Da Vinci surgical system. During the procedure, the device is mounted on a robotic arm and its waveguide goes through the patient. One of the major drawbacks of this device is its lack of maneuverability, which can cause several injuries to the patient due to the high temperature of the waveguide. This device is in fact not compatible with the end-of-race technology, which enables 7 degrees of freedom at the end effector, which is shown here. Moreover, the device is too large to be mounted at the end of a wristed-like joint and to be inserted into a laparoscopic port. Can an ultrasonic surgical tool be miniaturized to be mounted at the end of a wristed-like joint? So there are different strategies, two main possible strategies, and today we're going to focus on piezoelectric materials, although these two strategies can be combined. Ultrasonic actuated surgical tools are normally bolted Langevin-style transducers, BLT, where a front mass and a back mass pre-stress a stack of piezoelectric rings. Normally, hard piezoceramics, such as PZT4 and 8, are used, and these are held together by a bolt. The length of the transducer determines the device operational frequency, and this, to some extent, has an impact to the achievable vibrational amplitude. As shown in the graph on the right-hand side, the higher the frequency, the less the vibration, so the less the performance. To achieve the desired effect on tissue, ultrasonic surgical tools normally operate at 55 kilohertz, and this put a constraint on device dimensions. This will also result in a too large device to fit into a laparoscopic port. Can piezoelectric single crystals help in device miniaturization? This table shown here compares the key properties for resonant ultrasonic devices. PZT4 and 8 piezoceramics are compared against manganese PIN PMMPT piezocrystals. In these devices, the figures of merit are determined by IK-D33, IK-K33, and IK-QM. One of the advantages of piezocrystals is the fact that these properties are simultaneously achievable, while a trade-off between them is present in PZT families. This is shown, for example, in the graph on the right-hand side, where you see the trade-off for PZTs and straight lines for piezocrystals. The higher energy density of piezocrystals can be paraphrased as less piezoelectric material volume is needed to achieve equal device performance. And the higher elastic compliance means that the same vibrational mode is found at lower frequencies in piezocrystals than in piezoceramics. Some challenges in piezocrystals, however, are present, and these include the lower phase transition temperature when compared to piezoceramics, which may also alter the device functionality. In this study, we compared manganese PIN-PMMP Piezocrystal in a ring sample with peak 181, which is one of the best hard Piezoceramic on the market. Peak 181 is a modified PZT8, and hereafter in this presentation we will refer to it as MPZT. Few key properties of the rings can be highlighted, and these are, for example, for MPZT, which show IQM, a D33 of 253 and a K33 of 0.66, whilst manganese PIN-PMMP Piezocrystal shows lower QM, higher D33 and higher K33. One important thing to point out is that the resonance frequency of the Piezocrystal sample is half the one of the MPZT, and this is due to the higher elastic compliance. Moreover, the thickness mode of the manganese PIN-PMMP is not as clear as the one presented by the infinity symmetry Piezoceramic. However, this is believed to be suppressed in the assembled device. For this material study, we have chosen a simplified design space where the transducer is a conventional BLT with no gain profiles. Back and front masses are made in titanium and a steel bolt is used. This BLT was designed to resonate primarily at its first longitudinal mode at 20 kHz, corresponding to half wavelength. And it can also be excited at higher harmonics, for example, at the third longitudinal mode L3 at approximately 60 kHz. Devices were designed and simulated via on-scale FEA with a simplified quarter symmetry model, and a finer mesh was used for the transducer, part, including the piezoelectric rings and the electrodes. The model is electrically excited and then left to ring down. Transducers were assembled and the Piezocrystal BLT was found to be 9 mm shorter than the Piezoceramic BLT. Pre-stress was applied accordingly to Piezoceramic guidelines at 3 Nm, while 2.5 Nm was found to be sufficient for the Piezocrystal rings to stabilize the electrical impedance. The electrical impedance of the fabricated BLTs was characterized with an impedance analyzer and compared to the electrical impedance obtained through FEA. Good agreement was found for the L1 and L3 modes at 20 and 60 kHz respectively, with small discrepancies less than 3.4%. And this confirms the accuracy of the design and FEA steps. The design transducer show similar QM, and the Piezocrystal one present a wider bandwidth. 3D laser Doppler vibrometry was used to perform experimental model analysis to validate the mod shapes of the fabricated BLTs. Reflective tape was applied to increase the SNR, and the L1 and L3 modes were confirmed by both FEA and EMA. And results are shown here, for example, for the L1 mode in FEA and EMA of the MPZT, and for the L3 mode, for example, in FEA and in EMA. Further investigation was conducted on the stack deformation, and this was found to be larger for the Piezocrystal BLT, demonstrating the dispersion of useful longitudinal vibrational energy in the radial direction. This is believed to be caused by the crystalline isotropy and the crystal symmetry, which is 4 mm. Now let's move on to high power characterization to investigate the actual performance of the transducer. This shown here is the block diagram of the measurement setup prepared for these experiments. So there is a power amplifier and a signal generator which are controlled through a LabVIEW script to excite the transducers. Current and voltage probes allow real-time monitoring and the electrical impedance to be measured and obtainable at high power excitation levels. An LDV is also part of the setup, allowing the vibration velocity to be measured. Frequency sweep from below to above FR were performed in the range of 1 to 70 volt RMS, and the maximum vibration amplitude was measured at the BLT front face. The maximum vibration amplitude was found to be around 10 microns and 3 microns for the L1 and L3 modes respectively in both BLTs. As you can see, all the curves bend left, showing a nonlinear effect called softening, which can be translated as resonant frequency downshifts. This is a nonlinear effect present in all Duffing-like systems, showing, for example, nonlinear stiffness. Other nonlinear effects are present in the graphs, and these are, for example, the discontinuities. Frequency shifts were found to be larger in the manganese-doped Piezocrystal BLT. Electrical impedance magnitude and phase were also measured at high power using two different types of electrical excitation. The first one is continuous sweep, CS, which mimics effectively high power impedance analyzer with a frequency sweep as quick as 1 second, which can catch the transient response of the transducer. The second method adopted was the steady state burst sweep SSBS, where the transducer was excited with enough sinusoid cycles to reach the steady state, at which current and voltage were then measured and impedance calculated. These correspond to the conventional method to excite transducer for resonant applications. Up to 100 average were performed for each measurement, and gaps were considered between each excitation cycles to prevent and disperse heating of the BLT. Again, nonlinear softening and discontinuities were observed in the measurements, with, for example, transient artifacts, as this one labeled as A1, nonlinear softening and discontinuities at the steady state. To have a practical understanding of the result just shown, resonant anti-resonant frequency points were extrapolated from the previous graphs. This was done to compare both the excitation methods and the Piezoceramic against the Piezocrystal BLT. In terms of excitation methods, they were found to be very similar and equivalent in determining resonant frequency shifts. Regarding the assessment of nonlinearities between the two transducers, as is possible to see in the excitation range considered, frequency shifts for both FR and FA appear to be directly proportional to the voltage applied, and they're almost straight lines from the graphs. Linear fitting was used to quantify the frequency drops by calculating the slopes, and these were found to be larger for the manganese-doped Piezocrystal BLT. The mechanical quality factor was also measured at high power by using the transient method. This is performed by fitting an exponential decay to the second transient after the steady state time responses. Either the current or the vibration velocity responses can be used as they are equivalent. Measurements have shown that the QM remained fairly constant at high power for the Piezoceramic BLT for the L1 and L3 modes, while it drops about 70% at 70 volt RMS for the manganese PIN PMMPT BLT. In summary, Piezoceramic and Piezocrystals were compared in the actuation of a standard BLT. The two devices have been shown to achieve similar performance, with the manganese PIN PMMPT BLT showing wider bandwidth but larger nonlinear effects. The Piezocrystals have shown successfully to be able to shorten the length of the BLT due to their higher elastic compliance. However, the ring sample geometry might not be the best way to employ them due to the crystal anisotropy. Future work will explore the capability of these BLTs to cut soft tissue, and they will be excited by a commercial ultrasonic driver for frequency tracking and impedance matching. Thank you for listening. Please go to visit Sardinia whenever you can. It's an amazing place, full of nature and ancient history. I would like to thank my sponsor, the PSRC, for supporting this project, DNR for providing the Piezocrystals, and OnScale for providing a research license.